This is a derivation of the probability density function of the normal distribution without using polar coordinates. It uses starts with a simple definition and derives the density function of normal curves centered at the origin and uses the result that f of x minus the graph anyway of f of x minus k is the same as the graph of f of x translated k units parallel to the x-axis. It says a function y equal f of x centered at the origin is normally distributed if its rate of change is directly proportional to x and y. The fact that e of x or the expected value is 0 will become relevant later on, but because it's an even function symmetric about the origin, the mean or the expected value will be 0. So from our definition, we could form the differential equation dy dx is equal to minus kxy. The rate of change is directly proportional to x and y. The use of negative k is just a matter of convenience because we anticipate that it'll be downward sloping. So the concave downward essentially. K is arbitrary anyway, so again, it's just a matter of convenience. By separating the variables, we get 1 over y dy is equal to minus kx dx, and integrating on both sides gives ln y is equal to minus kx squared on 2 plus c. That implies that y is equal to e to the minus kx squared plus c. By using laws of indices, we get the next guy, y is equal to e to the minus kx squared by e to the c. And of course, c is arbitrary there, so that e to the c could just be represented as a. That guy is what we're going to label equation 1. If this is a probability distribution, it means that the integral of that function from positive to negative infinity is going to give us 1. But it's also true that that's an even function. Essentially, it's symmetric about the y-axis, so that the area under the curve from 0 to negative infinity will be the same as the area under the curve from 0 to positive infinity. So you could just say that the integral from positive to negative infinity is just twice the integral from 0 to positive infinity, which is the result that we use there. This is just what it describes. It goes on to say, well, yeah, that guy, right? And well, we just kind of rearrange it to get equation 2. We're going to consider the integral on the left, this guy in particular. It says consider that using substitution where we let u equal to root k on x. Let me just slide up a bit. So u is equal to root k on x, root k on 2 times x. If we differentiate with respect to x, we get root k on 2. We transpose for the x, we get root 2 on k du is equal to dx. And well, as x approaches infinity, u approaches infinity. As x approaches 0, u approaches 0. Essentially, limits don't change. And therefore, your integral becomes that guy, root 2 on k by the integral of e to the minus u squared du from 0 to infinity. We label that guy equation 3. Now, what we're going to do is we're going to square this integral, essentially because it's tough to integrate e to the minus u squared. So by squaring the integral, evaluating that integral, and then taking the square root, it gives us the value of the integral that we want, which is what we have in purple here. All I'm doing in green is I'm just using a different variable. So because u is a dummy variable, it doesn't matter whether you use the variable u or v or any other variable. So that's all I'm doing in green. Instead of using u, I'm using v. But what that allows us to do is form a double integral. So in my mind, I don't love the double integral, but I feel as though if you just think of it as integrating with respect to u and treating v as a constant, and then integrating with respect to v and treating u as a constant, that gives us the exact result as what we would have up top. So for me, again, it's not super comfortable, but I feel as if you can, at least for me, when I think about it that way, it kind of sits comfortably in my brain. So that is what we're going to do. We're going to make a substitution of vt for u. So we let u equal to vt. Remember, we're going to treat v as though it's a constant. So t is a variable there. If we differentiate with respect to t, we get v. We transpose for du, we get du is equal to v dt. And then as u approaches infinity, t approaches infinity. As u approaches 0, t approaches 0. That clearly is the case. Limits essentially don't change, which gives us this guy when we make our substitution. just using laws of indices and factorizing minus v squared there, we get the expression in green. And then what I want is an expression in the form f prime x e to the f of x. So that's what we're doing here. I'm essentially just introducing a term that will kind of allow us to arrive at that result. In particular, minus 2 by t squared plus 1 in the numerator and denominator. So we end up with the thing that we want, which is f prime x e to the f of x. We integrate, we get it in the form e to the f of x. And then when we evaluate that integral, uh, as t approaches infinity, that expression approaches 0. When t is 0, it gives us 1. So essentially, we're multiplying by negative 1. We get a nice positive result here. I'm just factorizing a half, where the integral of t squared plus 1 is just going to give us tan inverse of t. As t approaches infinity, tan inverse of t approaches pi on 2. And when t is 0, tan inverse of t is 0. We get nicely pi on 2. We multiply, we get pi on 4. Remember, that's the square of our integral. So it tells us that what we want to get is the integral itself. We take the square root. Our integral becomes root pi on 2. Sorry, root pi on 2. It says substituting in equation 3. So let's just slide up to equation 3. So essentially, we want to substitute for this guy. But let's just take a look at equation 3. So we substitute in equation 3. We're just replacing this guy with the result that we got below, root pi on 2, to give us this. So it says the integral of e to the minus kx squared on 2 from 0 to infinity is equal to root 2 on k by root pi on 2. We simplify. It gives us this guy, which we'll call equation 4. And again, we're going to make another substitution up top. If we slide up, so it says substituting 4 in 2. We're going to take a quick look at 2. And essentially what we're substituting for is this. So that's what we worked out at the bottom, which is, here's a substitution, that guy, root pi onto k is equal to 1 onto a, and that allows us to transpose for a to express a in terms of k. We go ahead and substitute that result in the first equation, equation 1, where now we would have an equation in terms of x, but no e, right? So we have nicely just our arbitrary constant k. So we just made the substitution for our a in equation 1 here. Right, so we have it nicely in terms of just k. And all we're seeing is, well, we're trying to describe a probability density function. So we're just going to call it nicely p of x. On page 2, we label that p of x equation 5. And we're just using the definition of the variance. So the variance sigma squared is equal to e of x squared minus e of x all squared. We said at the beginning, because our function is even symmetric about the origin, our expected value or mean would be 0, this guy. So it tells us that our variance is just e of x squared, which is just the integral of x squared p of x from positive to negative infinity. We put that in, you get the guy below. And well, this is the same type of thing as before, where this is even, it's symmetric about the y-axis, which just tells us that the integral from positive to negative infinity will be just twice the integral from 0 to infinity, which we have there. We just factorize the constants, and then we're going to use integration by parts, where we let u equal to x. Of course, the u dx there gives us 1. Therefore, the v dx will be x e to the minus kx squared on 2. We integrate that guy to find v, where our expression could be written in the form similar to before, f prime x e to the f of x. So by introducing that minus k in the numerator and denominator, it gives us what we want. So we integrate, it gives us our result in the form e to the f of x. Therefore, v is minus 1 on k e to the minus kx squared on 2. We go ahead and make our substitution in here. So we have a constant hanging out front. That's where we're going to apply our integration by parts. So it's now in the form uv minus v du the integral rather of v du dx. where this is our UV, where if we evaluate, we're going to get as x approaches infinity, that expression approaches zero by using L'Hopital's rules. Fairly straightforward. You can check it yourself, but if you apply L'Hopital's, it gives you zero for the first for the upper limit, and then for the lower limit, easily you're going to get another zero. That gives us nicely a big zero there, and it means what we're left with is essentially the guy on the right hand side, this guy, so that well, it's just a matter of evaluating where. It tells us that we're substituting equation 4. If you remember, but we worked this out already. That is just root pi into k. You could go back and check, but that's what we got. And then if we substitute, simplify, what we end up with is just 1 on k. Basically, everything kind of cancels there to give us nicely 1 on k. We transpose for k. We get k to be 1 on sigma squared. That allows us, therefore, to substitute for k as 1 on sigma squared in equation 5. Well, equation 5 is just up top. Hold on. So substituting for k here and there is going to give us our expression with no k, just sigmas. So that is our guy. So this is our probability density function for normal curves centered at 0. And then we're just going to use the result that we described at the beginning, the fact that f of x minus k is just f of x translated k units parallel to the x-axis. It says for all normal functions, big F of big X centered at an arbitrary mean mu, x is equal to x minus mu. So if we just replace our x, let's say, with x minus mu, it gives us our guy. We basically just replacing our x there with x minus mu. We're calling it big F of x, and it gives us 1 over sigma root 2 pi e to the minus x minus mu squared over 2 sigma squared.